All right, today let's talk about z-scores. In some way, we have been building up to this. So z-score is really, it's used in statistics quite often, but it's really a relative measure of a data point to its data set, or relative to other data points in the data set. Where does the point we are concerned with lies? That's really what z-score is. Let's try to build the intuition behind this. Okay, all right. Suppose, and this is something we have always seen, and we'll try to build it up a little bit better. What does it mean when somebody says, well, suppose our data set is normal? What are they, when people make this graph, what are they really making? Well, remember, we started this class talking about a measure of centrality, right? A measure of centrality, and we call it mean. Let me write it x bar. I'll replace sometimes here with mu. The only difference is mu is for the population and x bar is for the sample. From now onwards, I'll try to use use one for the other. It really, the difference is very subtle, but we'll be fine using any symbol when the difference is not required. The next, we had a measure of variation. We liked both variance and standard deviation, but we really said standard deviation is in the same unit of the mean, so we'll keep with it. So the z-score, or any data set can be described, at least the first two moments of the data set can be described using these two variables, these two parameters really, the mean and the standard deviation. Okay, and that is what you are drawing when you draw this curve, this normal distribution curve. That's what you're really drawing. What you're saying is, this is your mean. The highest point is our mean. The reason it's the highest point is this. Really, one thing you forget is, in this y-axis is the frequency. So the fact that your mean has the highest value in your y-axis means it is your most frequent variable. In your data set, your mean is most likely to be most frequent. Another thing you will see is it at the center of the data, right? Half the data is left of this mean, half the data is right of this mean. Exactly why the reason we call the mean as the measure of centrality of data fits right away. We also said mean is the most likely data point. That's why it has the highest frequency. And we don't need to know exactly how much. It depends on how the data is distributed and that will be defined by your variation. But one thing we are for sure is it's the most frequent data point, or at least expected to be. Now, one thing you have to know is your normal distribution could have been this. Your normal distribution could be, let me use another color here, it could be this. Well, what separates this normal distribution from this normal distribution is it has a low variation. Well, that makes sense, right? If this is your mean, on average, your data is distributed between here. Your data is not distributed too far like this graph. That means how flat or how steep your graph is really depends on your variation. Again, this graph, people have been, we draw it all the time, but what is this really is? This is the assumed frequency. What you're really drawing when you're saying this is, suppose my mean is 10, and suppose this is, say me number is say 5, and suppose this number is 15, right? The frequency of you seeing a 10 is high, and we don't exactly need a whole, when we use the relative frequency. So what we say is, suppose the sum of all the frequencies of all possible numbers is 1. That's what we assume. No matter what that is, we assume this 10 to be the most frequent number. The further we go from 10, they become less and less frequent. That's what you're really drawing. We ignore this y-axis most often because it's understood what it really is, but that's what is happening. All right, with that in background, let's try to understand G-table. So you have infinite combination of mean. I might write x bar or I might write mu and sigma. Right? Infinite combination. Your x bar mu could be, or your x bar could be 10, it could be 10.1, it could be any number. Your standard deviation could be any number too. It could be 5, it could be 7, any number. Right? I mean, that just depends on data. You don't have control over it. But we want to use this to define, the location of any data point. Now, intuitively, that should be possible because suppose if this is 10, this is mu, or x bar, this is 10, and you have a standard deviation of, say, 5. So the notion is, this is telling you the centrality of the data set. The whole data revolves around 10. That's what it's telling you. The standard deviation is telling you, well, on average, how the data is distributed. So you should be able to tell me, where is this, say, 4 located? Or another way to say, where does this 4 lie relative to other data points? Or another way to say, how many data points are left of this? How many points are right of this? Again, you can do the percentile calculation and all these good things, but there is a very standard way of doing things, and the trick is this. The trick is, we made a standard table, and we sometimes call it standard normal. Okay, standard normal. These are called normal distribution, or distribution which has this property of mean and standard deviation, and this has this nice looking graph, and the mean is at the center with the highest frequency, and half is on one side, half is on other side, and this is symmetric. We call this normal. But we created one very, very, very standard normal distribution, if you will. That standard normal is nothing in it. It's not a unicorn. What it is a normal distribution which has a mean of 0, and a standard deviation of 1. Okay, and this could have been any number, but this is a really good choice, and I can show you later why this is the best possible choice they could have chosen. After they chose this, what they did was they made a table. Well, they made this table, that is your G table at the back of your every stats textbook. Somebody calculated, okay, left, so remember, this is 0, and this is standard deviation is 1. For every value, so the left of 0 is negative values, right of 0 is positive values. So let me change the color here. And then they say calculate, okay, left of -1. Okay, so many percentage of values are there. Left of, say, 3. So many percentage of values are there. Say 50% of values are there, or 40% of values are there. They came up with number. Well, first thing you know, because this is symmetric, 50% of values are left of 0 and 50% of values are right of 0. All right, and similarly, the G table will tell you what percentage of value is left of 1 and what percentage of value is right of -1, and all this. Okay, with these two things in mind, now what it is, okay, for this one particular standard normal distribution, you have this table made. This 2 pages long a table made for you. Well, one thing you could do is you could make a similar table for every possible combination of mean and standard deviation. Right? You could do that. But that sounds pretty stupid. I mean, you'll need a really, really big textbook just of normal distribution telling you, for the combination of mean of 10 and a standard deviation of 5, so many percentage of value lies left of 4 and right of 4 and all these things. Right? Instead, what somebody figured out is find the equivalent of any normal distribution to the standard normal. Let me make this picture a little bit better. So what this idea is okay, we already have a table for a standard normal, right? A normal distribution of mean of 0 and a standard deviation of 1. For this, everything is plotted out. For every value say minus 1.5, minus 1.25, minus 1. every combination you can think, every value in the number line you can think of, somebody already calculated what is left and what is right of it. Now you are interested in this particular another normal distribution. Well, right, suppose you are interested in this normal distribution that has a mean of say 10 and a standard deviation of 5. Again, this could have been any two numbers. One way is to make a table for this. But how many tables you're going to make? Instead, as I said, somebody already figured out, you give me a value. You give me a value, say, I want to find what percentage of values is left of 7. In this distribution, remember, mind you, not left of 7 in any distribution, but this particular distribution, which has a mean of 10 and a standard deviation of 5, I want to find out what is left of this and what is right of this. Well, somebody figured out a way, what is the equivalent of this 7 in this normal distribution? Well, as soon as you figure out the equivalent of this 7 in this distribution, then you can refer to the table and find out. So suppose the equivalent is, say this value, equivalent value is, I don't know, 0.5. I'm just arguing, 0.5. Then if you know the equivalent value is 0.5, you can go to the table and find out what is left of 0.5 and right of 0.5. So that is what G is. The equivalent of any normal distribution in this special normal distribution, what we call a standard normal, is called G. Let me stop this video here and come back and show you the math.